Hello everyone. So I am Kuldeep Jivani. I look after AI solutions at Concert AI. It's an oncology company. So I am like a researcher at heart. So I love to go deep into like technologies, mathematics, and that's why like I go deep into like how LLM works and different technology works. I just want to share my research with all you guys so that you can also use these for your own applications. So I'll start with some good quotes. Let's start with the first one. It says it's not enough for AI to be right, but really, why? So interesting part is like AI is getting lots of traction. So it's getting really important. Every technology company is now using AI, right? So all the workforce is exposed to AI, and they're all using this technology, and they're now also more relying on it. So it has to be more responsible. So because of that, it's not enough for AI to be right. It must know where it might be wrong. That's critical, right? Because we rely on something so much that responsibility increases. And because of that, kind of we have to make sure that when it's going wrong, we should know what should we do. Should we trust that? Should we do something else? And how we can tackle that. Saying the same thing technically, that quantifying uncertainty enables system not just to predict, but to know when not to. Like when to hold back and say, maybe require an SME or require an input to rectify. On the same front, uncertainty, right, is also a way to explore, kind of to know where to look next, basically, which areas are kind of uncertain, which areas have loopholes. So it's like a good tool to build like more reliable systems and make sure that when we enter into the world of AI, they are like more tangible and they're more reliable. For this thought, I'll just show you the agenda I'm going to talk through. So as I was telling, right, I believe more in going deeper. So I'll quickly tell you about like how things are. The key part is I believe in knowledge. Like knowledge is the key for gaining information. So I'll start with like how LLMs work, give you like a high level picture, just to know that what's happening inside. And how can we like use that to capture some things that's useful for our applications. I'll talk about hallucinations, why do they happen, and what's causing them. Then I'll talk about SLMs, small language model. They're really a powerful tool, but actually they got like lost traction because of the popularity of LLMs. But they're a very powerful tool. I can just tell you how they'll help you in solving your things in a much reliable way. Then yeah, I'll talk about LLMs, how do they work. Then talk about like 3 categories of LLMs, like black box, where you just get the answer right, nothing more. And like some commercial LLMs, some open source LLMs, like ChatGPT. ChatGPT also uses probabilities, so that's like a gray box LLM. And then white box means they are open source, like your LLaMAs, Mistral, everything. So as you have more information, you can do more things. So with that, let's just start the topic. So let's start with this famous picture. So this is basically from Google's paper, attention is all you need. So the key idea that they started in 2018 was basically language translation. They like use both encoder and decoders to see how they can convert the language perfectly. Later on, I think they were used separately, like encoders separately, decoders separately. And in this picture, you see you have like a self-attention in probably the encoder part, your mask attention in the decoder, and like a cross attention to correct both. But later on, right, when we use separately, we just had like masked multi-attention in the decoder and like the self-attention probably in the encoder. Just to look at the application, right, I'll just talk about this at a high level picture, that what they do. So like I'll talk about encoder first. In encoder, we can like attach heads, right? One, we can get embeddings for data. So that embedding can be used to build things like RAG relation, right? What we just saw earlier also, that how to retrieve documents, how to get semantic similarity. So that's one good application. Then we can add more heads. So like one could be like the token classification head. That means each token can be classified, right, into some classes, what do you look for, be like persons, people, all those things, like in NER, or name entity recognition. That's second application. Then you can also add another head called the sequence classification head, that you can classify entire sequence, like in case of sentiment analysis, like is it positive, negative, or maybe any like notion for the entire text that you want to talk about. Then there are more applications like relation extraction, and then probably your something called APSA, or aspect-based sentiment analysis. Which means like, for example, there is a like restaurant review, that the food was good, but ambience was bad. So the sentiment is mixed, right? But if you give an aspect or a topic, So for the food, it's positive. For, let's say, the ambience, it's negative. So it's like a mixed thing. So aspect can give you like a focus area within a text, right, what to focus on. So this way, you can build niche applications which are more focused and more reliable for applications. Coming to decoder part. So like here you get from embeddings the vocabulary, right, the words back, and then a distribution of words where you now predict the next token. This is basically how generative AI works, and we keep getting tokens based on the tasks we are given to the LLM. At a high level, right, again, like things like generative AI applications, you see a lot, they're built on top of them. Then you have these like LLM agents we just talked about, and like then you have like code gen, vibe coding, that's getting very popular. Then you have like these Q&A and many other applications. So at a high level, I'll just take a pause here. I'll come back to this picture later on, right, to see how we can use these individual parts, right, to extract information to find uncertainty. I'll start with an example first, right? How do you normal work, like LM work? So I'll give a simple task, right? It's a simple prompt. It has like two parts, right? The above part is system prompt, second is user prompt. It's a simple thing, just convert a sentence from past tense to future tense. A very simple task for LM, right? Below the sentence, it says, she played the piano beautifully for hours and then stopped as it was midnight. And then the second sentence. So task is to convert from past tense to future tense. I give it to like a LLaMA 3.1, 8 billion model. It does the job perfectly. It's a simple task for the model, and it gets it right. But as you know, right, there are lots of conflicts with LLMs, right? Something called temperature and top P. So they are like used in different applications for different purpose, right? There is no single answer for a single temperature or top P. Like you want to do a creative generation or maybe like a more objective task. So they have different values to utilize. I'll rerun the same prompt with different value of temperature and top P and like show you what happens with them. So this is the next response, right? So this is like some temperature top P, I get a response. If you look at this, right, in this, the word is incorrect, right? It's not really future tense. It made a mistake. So although via inspection, we can find that, but we'll see how we can find this mathematically, right, using some of the internal features. I'll show you another response, right? Here, it's a more varied response, like it says going to stop after midnight, added more information, missed the word, let's say, wearing a cap. So got a bit more, I would say, like berserk. There is even more, right? It totally goes berserk, right? Adds close information like 2 o'clock midnight and like we do many things. So it goes on. So that means, right, depending on the condition you set, it can go like exactly what you want to do or do different things. So that's like hallucination. And the key idea is how do we catch this, right? Without looking at that mathematically by some metric or a score or automate those things. So that's the key area, how we want to find and tackle this. So I'll just come to this and now show you how it works, right? The first thing, probability, right? Because that's how the model understands, right, what the words are. It's like a calculator. It's a mathematical calculator of words, right? It looks at the word by probabilities before that, after that. So the tool to convert like token to probability is SoftMax, right? That's a simple formula you can see on the screen. Logic score you get from the model. It's normalized by this HTML power divided by sum of all, and you get the probability. As simple as that. Let's say, right, we have a token prediction, right? So we are predicting tokens like some 24, 15, 33. There are some tokens. And as you were telling earlier, they are like obtained from a distribution, right? Probability distribution. So for each of them, there is like a choice, right? So let's say like LLaMA 3.18b, it has 128K tokens. It has to choose from one of them, right? For each token. So it assigns probability to all of them. So like in this case, right? For 24, there was a choice, right? 15, there was a choice. And let's say we do a very simple strategy, like a greedy search. Pick the one with the max probability, right? As simple as that, no fancy stuff. So we select these tokens based on strategy. Now, that's a very usual thing, right, to do. Most of LLMs do this thing, right? Some can use sampling, other things, but that's a popular thing. If I just plot them, right, the probabilities of predict token on a simple graph, it's like a density graph. What it says that maximum probabilities, right, are concentrated on the right side, that towards like 0.95 and towards 1. And this is not really unique, right, to this solution. It's typical thing for most of the answers, right, that you get probabilities at a very high level. So this is typically happening with LLM, right? So more than 90% are above 0.9. It's not a flaw. It's like a mathematical shortcoming of SoftMax. By design, it's like over skewed towards one side. So that's the limitation of SoftMax. And that's why we require scaling, right? That means how do we correct the probabilities? So, and this is something if you like look at data, right? You'll see very often in any of the prompts, right? So they are correct. They are like likelihood, but not into probabilities. They're not calibrated. So for calibration, there are more techniques. I will not go deeper into that part, but give you like one example. I'll talk about temperature scaling, right? So the same formula, if you just divide by T, right? That's it. So people would say, right, is that it? How would like a dividing by t make a difference? So let's look at an action, right? I can take an example. So from the prompt I had earlier, I pick like one of the response over there and just plot the logis, right? Look at this plot. It's like a logis score, right? Going from -10 to +10. At temperature 1, there is no scaling. Now, if I convert to probabilities, right, by applying SoftMax and computers CDF, that's like a cumulative distribution function, or like adding all the probabilities. So the graph below means, right, if you look at a vertical line, so the x-axis is like tokens, right? It goes from 0 to 128K. So there are 128K tokens in LLaMA. So each token is adding a probability. There are like 6 to 7 vertical lines. That means only 6 to 7 tokens had a significant probability, rest were like 0. That's why the flat line, right? So flat line means they're not adding any probability. So if I just like change value of temperature, like let's go to like 0.3, 0.1, as expected, right? It just scales down, right? It goes to like 3 times and 10 times, right? Nothing fancy about that. Similarly, if you like go from 2 to 3, it goes to half and kind of like 1/3. So the key part is, right, if you're just scaling the number side scores, how will that affect in probabilities? So I'll take a pause. So what do you guys think, right? If we take like temperature 0.2, 0.3, 0.1, how will the probability plot look? Can you even make a guess what you want to see, right? Like in the center plot, how will that change? Any guess, anyone? More? Yeah, more spiky, I would say, right? Yeah, that's correct. So like 0.3, the steps are going on, right? So steps are decreasing. So you have less steps, and like in 0.1, it's a single step, right? So that means one token got like the max probability, right? It was very spiky. What about converse? What do you want to take a guess? What happens on the other side? If you increase temperature, what will happen? Smaller steps, I would say, right? It's like more like an inclined line, right? More like uniform distribution, like everyone's contributing. So every token is adding to the probability. So it's like an equal distribution. So there are two extremes, right? One is like a single token adding probability. Second case, all are adding, right? So that's why you can control the probability side of SoftMax. And yeah, obviously there is no like single value of t, right? That's the best value. Again, you have to find like what's a good t for you. So there are techniques to find those things. But with this thought, I'll move to the next lever, right? That's the top p. Just to give you an idea. So just give you points for temperature scaling. Like the key points, like if we have probability, right, it preserves order. Like for example, if Pi is greater than Pj, then the temperature scale Pi is also greater than Pj, right? It doesn't change the order. But there are two levers, right? Temperature greater than 1 is called like heating, less than 1 is cooling. So that means when you have like temperature more than 1, right, it increases entropy. As you can see, right, you have more tokens adding to the probability, like uniform distribution. So that means we have more token sample form, right? We can go more variance, right? It can go more creative, find many options, right? So that's good for creative solutions. Vice versa, right? Temperature less than 1. This is entropy is going down, right? Decreasing entropy. Probabilities are more concentrated. This means that we have less token sample from. So kind of your like window is changing because of these values. So this is something that you can control, right? Again, change for different applications. But yeah, it's a good tool. Coming top P. So it's called like nucleus sampling. That means how do you choose like a small nucleus, right, from the entire list of tokens available to you. So in this diagram, right, there are two diagrams, left and right. One is saying basically the sorting all the tokens with probability, right, for some prediction. Second is another case. And the purple line is like the CDF, right, just adding the probabilities, that's it, nothing more. When I say like top P equal to 0.8, it simply means cut off the like cumulative graph at 0.8. Or like make a like a horizontal line that just cuts it off. And the point of cutoff is basically where I choose my tokens, right? So in the first case, I get like 7 tokens. And in the second case, I get like 3 tokens. So like same top P, different distribution, I get different words, right, to sample from. With this idea, let's come to the like key part, example, right? Look at my example, it made a mistake, like in this example, right? The word is was wrong. Now how can I look at this thing like from a numeric point of view? So let's zoom in, right? Again, I'll show you how these things work, right? Let's zoom into sentence, first sentence, look at token by token. And as I was telling you, right, they work on distribution and choosing a token, right? So let's look at the first word. This grid says, right, these are the top 5 options available for the first answer, right, first token basically. Green color means they were eligible by top P. Look at number, right, the first value is 0.949. It is less than the top P set above, right, 0.95. That's why it chose 2 tokens which are eligible, right? It has to sample from 2. How? There's something called multinomial sampling. I'll just give a quick idea how it works. So like let's say you have a number line, right, between 0 to 1. We normalize, let's say, 0.959 to 1. Then I have like a 2 choice, right? Region 1, region 2. I take like a random number generator and like just try to guess any number. If it lands in the first part, it's my first token, second part, second token, right? So because probability is very high for the first one, 99%, the first got chosen, right? So this way, like you choose everything. I just go with the rest of tokens, right? What happened for them. And if you observe, right, in each of them, there is a single choice, right? Although top is 0.95, very high, still I don't get choice. That's by nature, right? Because of SoftMax, probabilities are always higher. That's by design of all the LLMs, right? So you don't get choices. So although high top P, still you get not choice. But let's come at the next word, right? Stop. Here there are 4 eligible tokens, right? That can be chosen from. But again, by probability, right, the first got chosen. That's by chance, right? Again, next one, there were 5 tokens eligible, right? The first got chosen again by chance. There was no choice next one. But look at is now, the interesting token. There were 2 tokens, right? The will had a probability of like 0.8. Is was lesser, still got chosen, right? So this was by chance that happened, right? It could happen because probability is given probability, right? So although it was like less likely, but could happen. So that means these are like calculators. We are underlying working probabilities. So by chance, you can definitely get different words which are less likely also. So this means by knowledge, it knew the answer should have been will, right? But by sampling, it came to is. So these things happen, right? So just want to show that there are multiple things that's happening beneath an LLM that can cause things to go wrong. So with this, like, I'll take a different example. I like work in oncology domain, so we look at patient reports. It's like a sample report of a patient. He's like a lung cancer patient with some medication, right? So in this report, I'm just giving this report to LLM, and I'll ask, look at this report and tell me which are the cancer drugs, right? I'll attach the report to the LLM. It will look at the text basically and give me answer. So it gives me this answer, that these are the drugs which are like cancer drugs, and the rest are not cancer drugs. That's good, it is a good job. But actually, the option 3 and 4 are wrong. Because like dexamethasone is like a drug to treat inflammation, right? Although it's given with chemotherapy, because like it causes inflammation, but it's not used to treat cancer, right? So like in English language, say true, right, that it's like given for cancer patients, but not for cancer. So how do we like catch a mistake? The SME can catch by looking at it, but mathematically, how do we catch as a data scientist, right? So again, I'll just break this up into tokens to tell you how to solve this. So before that, I want to tell you one more thing, right? That it's also a function of training data. So I asked the same question again. Now this time I asked, give me all the anti-neoplastic. It's a technical word, right? Say same thing, cancer drugs. But there's a very specific medical term that means nothing else but cancer drugs. This time, if I ask again, it gets answer right. Because in the training data of LLaMA, this LLaMA model basically, LLaMA was trained on this text, right, of these cancer drugs. It knew anti-neoplastic means specifically cancer drugs and nothing else. So this change in prompt fixed the problem, right? But because of the condition that it knew that word, if that word was not part of training data, it wouldn't solve that, right? The probability would have gone down. So I'll just show you the same thing in terms of the words, right? I'll take 2 words from that, right? Cisplatin is a true cancer drug, dexamethasone is not, right? Let's look at tokens for these and look at the mathematical part. How does that work mathematically? So there are 4 tokens for this, right? Because it's not an English word, it has to break into smaller tokens and then look at them. So the first C, right, has the high probability, 0.9985. Rest are also high because like it's very confident. It knows it's a proper cancer drug, highly confident. Let's look at this next one, right? The first token is D. Interesting, right? Look at again. There are 3 eligible tokens, right? It chose second one again by chance. The probability is like 0.2 for D, what were high for Phil basically, but it got chosen. And next was like just like consequence because like D was chosen, they has to come to dexamethasone. So again, this happened like again by chance. If you run again, it may choose some differently. So these things happen like again LLMs. Function of both your training data as well as sampling. Let me show the same case for the next prompt, right? When I asked the word anti-neoplastic. In this case, cisplatin was again high confidence, right? No issue with that. So all high numbers over there. Let's look at now dexamethasone. So this time, right, the probability is perfectly high, right? No choice, very clear. This time it classified it as like a non-cancer drug. So this was sure it was not anti-neoplastic and was very high confidence and was working perfectly fine. So in short, like you can modify these things and observe. These are like tools to see, right, how things are working underneath and what things can help you for them. So with this, like I'll just like conclude this part and come to like SLMs, small language models. This is like paper given by NVIDIA. So NVIDIA says like these are like the future, right, of agentic AI. Why? Because like SLMs, they were really powerful from the beginning, right? That was Google's first paper, like BERT, all those things. But they lost like traction because LLMs got popular, right? You got so many applications out there, ChatGPT got popular, but they got left out. The key part is you can control them more, right? So they are more powerful. So these like encoders and other systems, they can actually do tasks very specifically. So I'll talk about them, right, just to show an example, like how they are different. So at a high level, I'll just tell you, right, when I talk about a generative AI LLM, so this is like a function of many things. Like for example, like how was it trained? We're trained like medical data, general English language, right? The domain expertise makes a difference. Then like training quality, like what was the human feedback on that? Was it like, what kind of training it happened? Then like what prompt did you give? What was the input data? What's the quality of data? Then like the sampling strategy. If I break it down, right, into simple steps, so like when you choose like the first part, like training data and training quality, you get a model, like a LLaMA, a Mistral, so that's what you get a first step. When you give like a instruction, you get like a small m or like a dynamic model or a circuit in that LLM that is doing your task, right? The intent that you give, it's following that. That small m, when given with input data, like in this case, like that medical text I gave you, right? The clinical note was the input to it. It used that to generate a PD, probability distribution. Now, based on my strategized sampling, I choose a token, I get next token, right? So if you see like these four things work independently, right? And uncertainty can come at any of these steps. So it's a more complex process, right, happening in LLM, in a generative LLM. So that's why it's higher uncertain. On the contrary, like the encode SLM, right, it's a very simple function. You have data, you know the, let's say, answers, train it, do a good process, right, to verify it, and you get the answer. So by design, it has like less uncertainty to occur because you can control it very better. So as a simple solution, right, if you have a like option to do like an objective task, objective mean like when we want to find entity, like I want to find medications, like find biomarkers, right, where there's a clear task defined objectively. In those cases, SLMs are better. But unless you want to find like a, more like a create a poem, right, that's not a purpose of this kind of LLM, right, SLM. In that case, go to LLMs. So depending on task, for objective tasks, I think it's good to go to these SLMs. So, but are they also perfect? Not really, right? So if you look at like an example of an NER, right, entity recognition, for let's say finding the medication, right, we can define groups, right, and like find them. So let's say I have an example, patient takes cisplatin, which was previous example. I sent to this NER SLM, right, it can give me tags, like was it like an other word or a cancer medication, was the beginning or intermediate part of that word basically. So that's, it can easily classify. Similarly, I give sentence like a dexamethasone, it can clearly say, was it conmed or a concomitant med given along with cancer meds. So it can classify precisely. If I have data, it's very easy to like classify things and have less kind of uncertainty over there. So with this, let's have the same report, right? Run the report by SLM. I define the classes cancer med, con med, other, right? Very simple. It colors everything blue. That's like other words, and have like two words coming as like cancer drugs, and other are basically by con meds. So clearly defined task, objective, it can capture really easily with less, I would say, ambiguity. But are they also perfect? Not really. They also have uncertainty, right? So I'll talk about uncertainty for these SLM first, right? Then come to LLMs. So talking about uncertainty, right? The idea of uncertainty is that I'll just talk about the concept of confidence first, right? Because people confuse confidence with uncertainty. They use like interchangeably, but they're not the same. Confidence is like a probability, right? Or model's belief in correctness, right? The probability you give from, let's say, the like class probability, the probability of cancer med, probability of con med. So that's a confidence. But uncertainty is a bigger concept, right? It's about how sure the model is about the prediction, right? About the ambiguity. Is it like auto distribution or whatever can cause that to be not sure? So in short, it's like an index to measure surety of the model. So it's a broader concept more than confidence, right? In short, LLM can be confident, right? Probability could be very high, 0.9 and 0.95, but still could be uncertain or possibly wrong, right? That's hallucination, basically. So uncertainty, right? There are two types of uncertainty. We can't solve everything. One is called aleatoric, second is called epistemic. So aleatoric means uncertainty due to data. Like for example, data itself is ambiguous, right? It's not clear, was really he had cancer, not cancer. That's a complex data, we can't solve that. But epistemic uncertainty, that means it's due to lack of knowledge, right? Or lack of training, or maybe something not good in that model. So this is something you can measure. So we'll focus only on the epistemic uncertainty. That's basically how do you find flaws in modeling that you can rectify or catch. So I'll focus on the second part, right? Epistemic uncertainty. And I'll just show you how SLMs work under hood, right? I'll get this picture back, right? We look at this picture in the beginning. That's the encoder that we had. So how does it work? I'll give you a small like view of things these layers are, right? How they're working. Then we'll like use them to actually find uncertainty. First step, right? You give a sentence. you get tokens, right? So tokens are converted to like a token vector, as simple as that. Then you convert them to embeddings. So you have like a embedding weight matrix that converts to like an internal embedding space. You get X, right, your input vector basically. Then you go to something called positional encoding, right? So like sinusoidal encoding, other embeddings are there basically. It adds the position information to the vector. You get like X pose, right? Then you use the multi-addition head. So the key thought over here is important that there are multiple heads in an SLM or LLM, right? If you look at that, what they do, they like divide data into chunks, right? Each chunk is given to each head. So that means like each is doing operation. That's like the self-rendition, which is like your popular QKV query format, right? That you do a dot product of query NK and then like normalize by square root D and then dot apply SoftMax and then V. So this is now like, again, they are like vectors, just a mass operation, right? While training, you learn a weight matrix, right? WQ, WK, WV. So based input, right, while you're training, you are learning how these queries, keys, and vectors look like, right? And then you can use later on. So later, just normalize them, right? Add the expose back to like avoid the issue of exploding gradients so that gradient don't go down to 0. And then like apply the MLP, multi-layer perceptron. It like goes to higher dimension, right? Based on your task, it then first goes to higher, then go to dimension D as per your embedding vector, right? And normalize again, and you get then the answer. In case of embedding, you get a vector, right? For your RAG application, basically, for each word you have a D-dimension vector that you can use to your semantic query, right? Semantic matching, cosine product, that happens. For token classification, you have like a class for each token, right? In case of sequence, you have like a single answer. So with this thought, right, I know it's like too much things out there. We look at the practical part of it, right? How can we use this for our uncertainty? So there is something called like a Bayesian approach, right? That's very powerful. I can't talk about why they are good, but assume they are good, right? And there is a technique called MC dropout that can basically help solve this very easily. I'll just come to that quickly. Like for finding uncertainty, you need distribution, right? Basically, is it like distribution more flat, more constrained, right? If it's more variance, it's uncertain, right? So the question is, how do you get probability distribution? Because by design, right, all neural network don't do distribution, they give answer. Like given X, you get answer, right, Y1 or Y2. It's fixed, deterministic. So this can't help finding the uncertainty, right? One way is you do an ensemble model, right? Do multiple models and run the same input by all of them. But doing an ensemble is very costly, right? Because these are big models, right? You can't run too many models, train too many models. That's practically not possible. So there was a paper by a researcher called Yaren Gal. He showed that you can do the same thing by something called MC dropout estimation. That means, like, given the same model, right? Same model, just drop random neurons at time, basically. So what will happen, that the same model will give different answer at different point of time because randomly dropping neurons, right? So while training, it's also like a good technique to kind of do revelation. That means that if you drop one neuron, right, it can't rely next layer on that neuron. You look at more neurons to basically look information. So it spreads out into multiple neurons and your training is more like stable. It is like not you're biased towards something, not overfitting. That's one part. Correspondingly, during inferencing, now each answer is different, right? So that is giving you like a more variety of answers for the same input. So this gives you like a distribution. I'll come to it like how does it work. So like the same network, right? What we're doing, we're basically dropping, like while training, some neurons at random. We have a D percent rate, right? 10% rate or 20% rate. So the same training basically while happening will drop things random. So it has to like learn more precisely the same information with drop in happening between. During inferencing, same thing will happen basically, and it will give different answers for all these cases. I'll show you an example, right? So this simple sentence, it says like EGF value is 25 ml Mg, and he's EGF positive. So second is like a biomarker, that's a property of a patient, right? First is a lab test, a blood test basically. Same spelling, but different meaning, right? Different context. And in this case, the model was like case insensitive. So it could figure out like, couldn't make a difference between lowercase, uppercase, right? For it was same thing. So I ran the model, like it gave me 2 tokens, right, for each of them, and say the token ID is same because it is like case insensitive. Answer is same for both biomarker, right? The first is wrong, second is correct. So the probability is very high, right? Because probability is 0.997 because it was trained that way, that while training, they marked all EGFR as like biomarkers. But then you like, there is also lab by the same name. So that got like a data corruption while training. But now how do we catch that, right? At this level, if you run again multiple times, you get the same answer, right? You can't do anything over there. But let's say we use like the Bayesian version, right, that we just defined earlier, and the same sentence, right? I ran with that model where I have the dropout enabled. In this case, now like look at this, I have like colored the EGFR lab as red and the correct one is green. Probability for the greens are all high, right? 0.97, 0.95, they're very high. But red ones are varying, right? 0.7, 0.5, 0.9, varying a lot. If I plot them in a plot, right? So left one is lab, incorrect, right is biomarker, correct, right? It varies a lot. Look at like, so like the X is probability, right? Y is density. So the probabilities are varying a lot for the lab one, but very less for the correct one. That's indication, right? Probably there's more variance. We can quantify them like by finding the mean. Mean is lower for the first one, higher for second one, right? So in short, like this variance gives me indication, more variance, more uncertainty, right? You can also define more metric like called coefficient of variation, like it's higher for the first one, lower for second one. So this way, right, you can also like get indication that is your answer reliable or not. So by simple like these, even SLMs, right, although they are very reliable, you can make it more robust by adding these things, right, using like a Bayesian version. And technically or practically, very simple, right? This is a piece of function, right, you call in your code. Give the input, call the model, you get the answer, right, logic basically. To modify, you just need one line, right, call model.train. By default, like in each BERT model, if you're using the original BERT paper, right, they have a by default 10% abort rate. It was designed by the author side originally to have regulation. So by this line like model.train, it will activate, right, the dropout layer during inferencing and just run a for loop, right, as per a sample size, and you get like different answers each time. So you'll get distribution rate I was talking earlier. For the same sentence, I can get multiple answers and plot them to find variance, find variation basically. So this like simple piece of code, right, adding one line of code, you can basically get reliable predictions from even SLM. So with this, I'll just move to the next part, right? Yeah, I think same like ensemble of models, right, acts like the same way. So let's come to LLMs now. So LLMs, right, again, the key part, the structure is same, right? I don't repeat that. All this idea is same. Only last layer changes, right? We add like a last layer linear and SoftMax to convert to like a vocabulary and then to like probability distribution and sample it. But the new part is, right, the LLMs are bigger, right? They're very massive, multiple layers. So as you zoom out, each layer is adding more value. I'll come to that now, right? So like LLaMA 3.1 has 32 layers. So 32 layers, there's like a meaning to that. Let's zoom into that, right? So my initial layers, they're actually talking about like grammatical constructs. So for example, like part of speech, all those things, morphology, local syntactic patterns, right? So they focus on the grammatical part of the text, right? How do we basically extract information from those words? The middle layer is talking more about the semantic part, right? What's the meaning? What's the concept? What they're talking about, right? Objects in the text, roles, phrases. So more like an understanding of the text. Last layer, right? They're more about intent. What did user ask? Like, did the user ask for like finding biomarkers, like getting a summary? So the intent of user in the prompt is captured in the final layer. So with this like high-level thoughts, right? We can kind of use them to define uncertainty. Let me show you how. So let's come to uncertainty, right, for LLMs. As you know, there are like three kinds of LLMs, right? I was like first like commercial open source, that's based on like the pricing structure. Then there's something called black box, right? Black box means you give a prompt and you get back tokens, right? Nothing more. This information available. Gray box means give a prompt, you get tokens and probabilities, right? So now you can do something statistically, right? That's at least some information available that you can do like ChatGPT, give probabilities, right? So that's like one good thing you can use there also. White box or open source, right? You can get probabilities, grids, right, of the token probabilities basically. You can get like activation functions. You can get like feed-forward networks, everything. It's open box, right? You can pull what you want to. There is no limit to information. So with this, I'll come to each one of them, right? And start with black box first. So black box, right, you just have the prompt. So you can't do nothing, right? So one way is you can ask another LLM, right, to judge the response of the first one and give a score between 0 to 1, right? So you can use like three things to evaluate. What's the answer relevance, right? What's the context relevance and like given the groundedness. That means if you have like a rack system, right, you got a document, ask the question. So first thing is the answer relevant, right? The answer matches with the question. You can give a score from 0 to 1. That's the first thing. Then the context or document we provided, right, from the rack system, is that connected with the question? That's a score 0 to 1. And then is the answer based on the document I gave to the like LLM? That's a score on groundedness basically. I'll give you an example, right, of these three things. So I basically pulled a report from internet about article on carriers, asked the question, right, which field has the most exciting career opportunities? The answer was AI, very likely. I asked you to score it. If you look at the score, it just gives a score 1, right, for answer relevance, because it's a very relevant answer, right, perfectly aligned with that document. That's why the content is 0.95. That means document says the same thing and answer says the same thing, right? Groundedness 0.67 because maybe it says more things, it's not talking about other things. That's why that is lower. Ask another question, right? What are avenues in AI? This time it gives slightly unclear answer, right? That talking about side projects, basically exploring various applications. It's a bit vague answer. Look at the scores. answer goes to like 0.5, right? But document is still relevant, right? It did not use that. That's why countedness goes down. But document is still good enough to answer the question. So another question, like what is right a job for applying? It gives a very long answer, right? Don't bother to read it. The key part is, again, answer is good, right? But not based on document. That's why like countedness goes down even further. So like this way you can evaluate like what is doing, how good the answer is, and basically is based on the document you're providing, based on probably the relevancy of that. But the high thought is that this, you need another LLM, right? And possibly a bigger one. Because, right, if you use same LLM, the issues, like same issue comes, right? So like for 8B model, I need an 80B model, right? So practically it becomes challenging because of like the cost and time. So although these are good measures, but yeah, less, I would say, effective in a practical enterprise version. So I'll talk about less on these things, right? I'll talk about the other things which are talked less upon. Let's talk about the gray box, right? We need probabilities, how we can do with the probabilities. So first thing, how do we get them? On OpenAI, there's a simple call, right? In your basically chat completion API, just add the word log props true, right? And top log props, that will give you grid. Like how much do you win? Top 5, top 20, basically. You get probabilities from chat API. Similarly for LLaMA, if you have the Hugging Face API, right? You can simply just enable like this output hidden states true and return they can generate, it will give you a dictionary of all the states and the token probabilities what you want. So like two simple things, you can get information from ChatGPT also and LLaMA also. So let's look at them, right? How to use them. One is like joint probability, right? Just take a product of all the probabilities by chain rule, right? And as you know, these are like conditional probabilities. Each token is like based on the previous tokens, right? So we can apply chain rule easily and get a single number, that's easy. Second is called perplexity. It's a popular measure, right? You'll find internet. It is a simple formula, right? It says take a log, take average, raised to power e. It looks complicated. Let me rewrite the equation in a simple way. It's just like a product of probabilities, right? Joint probability raised to power minus n, which means geometric mean, or geometric mean, nothing more, right? It's giving like a geometric mean of all the probabilities at a token level. Another simple thing called entropy, right? Just do a p log p, and I get an idea how diverse they are, right? So three very basic measures that you can do on probabilities, right? You just have probability. So that again gives like how much variance it contains, how much divergence it's diverging from like the base, and that gives an indication. Again, let's take example, right? The same problem I took earlier, right? Convert from past to future tense and look at the scores for the wrong example, right? So the first case, I have the wrong response, second is correct, right? So first one is making it like is, second is correct. Let's look at the scores. Joint probability 0.07, perplexity 1.5, entropy this, right? For second case, joint probability goes 10 times, right? From 0.007 to 0.07. Perplexity goes down, right? Entropy goes down. So simple thing, right? Without just knowing anything, just the probabilities are indicate, right? There was something wrong in the first one, but it's better in second one, right? So simple probability measures can also give indication that how things are like reliable, not reliable. So like we have one basic techniques, right? You can like zoom into this and look at a plot, right? This is like the tokens we saw earlier, right? Those 20 tokens we saw in the response, I'm just plotting them on probability plot, right? Y-axis is probability, x is tokens, right? I'm just taking 35 tokens which are predicted by the model and just plotting them. First case, right, in the wrong case, one token went to like probability below 0.2. Let's just tag them, right, annotate them. So the words, right, it was actually is, which was incorrect word, right? So the word got sampled from low probability and that's why it caused a mistake. In the second case, like the mean probability is not going anywhere, right? It's a higher range, like around 0.7 something. So if you can see, right, visually also, you can look at response, right? And with the probabilities, can know about what's happening inside, right? How they are kind of being treated by the LLM and is the loophole over there. So with this, I'll come to next part, right? Again, the Bayesian way, that's more reliable, right? But this time, we can't do dropout, right? Because dropout makes the process longer, right? For training, inferencing. LLM is bigger, right? If I'm doing dropout in LLM, it will take like days or months to train. So that's practically not possible. So we can't do dropout into SLM, right? That's only for SLM. For LLM, we can still like generate multiple things, right? I can ask the same question 10 times, 20 times, right? Multiple generation for the same question and then use that by a Bayesian way. Again, like two things we can do. One is like uncertainty at sequence level and token level. So simple thing, just a formula. Here, what they like is their case samples, right? Like for example, I took 15 samples. I asked the same prompt 15 times, right? Same question, same information, repeat like 15 times. And then LS like LK is a sequence time, right? Let's say 20 tokens, 35 tokens, right? And YK is a sequence probability. Simple form, right? Take the log of sequence probability, normalize by length, and take an average across samples. But the question is, how do you find sequence probability, right? Because there's so many tokens. What is the number that represents the probability of the entire sequence? As you know in the diagram earlier, right? The last layer is like the intent. Or in an autoregressive model, it gives me like the probability of the last word, including the conditional probability of previous word, right? So simple thing is just take the probability of last token, right? That's good way to find the sequence probability of the entire sequence. So that's one way to find like the uncertainty at like for the entire sequence. Token level gets better, right? If you have a grid for the token, right, which showed you earlier basically, you can like kind of find the entropy of each token, right? That is basically just P log P. For the grid, right? For each token, I get the P log P and like take normalize by length, take an average. So simple things, right? And definitely token level is more reliable because right, it's looking at the grid also, not just the token, pre-grid token. So that's more reliable. Again, let's look at example, right? These two numbers on the same example. So I run 4 versions, right? The same prompt, convert past to future tense, same sentence. I run it 4 times. But in the 4 version, right? So actually my case, 15 my case. I ran 15 times the same thing. Version is like temperature. So the temperature 1 is first case, 1.5, 2, 2.5. So same thing run at different temperatures multiple times, right? In this case, like uncertainty, right, sequence level is this number, like token level 0.07 goes to 0.5, 5.45, and like 10.7. It's increasing. That's natural, right? Because when you increase temperature, it diverges more, right? Hallucinates more basically. So logically, because I created that way, right, I knew it will increase, and I can capture that by numerically. So numbers are telling me that what I did by intention is being reflected in the numbers. So again, like one simple way to capture these things. So now, right, coming to white box. So these are the most popular, right? Because you can do multiple things, right? You have probabilities, probability distributions, you have like logics, everything you have, right? So in this case, again, simple, right? You have an API to enable it, right? So the last part, right, num-written sequence. You can like ask the LLM, right, to generate multiple response. This is very powerful, right? Because it is compute efficient. Because something called like KV cache, right? You can cache the key value and ask to run again, right? So it's like 10 times faster than calling LLM 10 times as compared to saying num sequence 10. So in less time, I get multiple response, right, and can do my processing. So in case of white box, right, because of many things. So I'll talk about few things, right? So first probability. I'll just take the same example again. That where probability is lower, right? It's like more diverse. So you can convert this to also entropy, right, at token level. So the plot below is like the entropy of the same like temperature 1.5. And if you can see, they are like kind of mirror image. When the probability goes down, uncertainty increases, right? Entropy increases basically. So both plots, right, and in 1.5, I have more variance, less in 1. So as I increase temperature, I'm getting more variance, and the plot shows the same thing. Another way to look at that is like the grid depth. So like in the first case, it says mostly I was selecting from the first topmost choice, right? But in 2 cases, it had a grid depth of 2, like 2 choices to sample from. In case of 1.5, I sometimes went to 4 grid depth, right? Sometimes like 3. So, but this gives me a picture that what was the choice given to the model. But this is not a true picture because like the probability also makes a difference, right? If the probability is 0.95 for the first one, the chance of selecting the first is very high, right? So we have to normalize this and look at it in the correct way, called the weighted depth, right? Just multiply the probability by the depth, right, and compute number. So that 2 becomes 1.1 and like the 4 becomes 1.4. So this like means like there is a 0.4 chance of like selecting more than a top one. So again, the higher that thing, the more uncertainty I can capture, right? These are like just graphs to know that how we can look at things visually, right? But if you want to automate, they're like different ways. So more technical way, right, is like something called scale divergence, where you can compare like 2 distributions. So between P and Q, it's the metric, right, to say how similar they are. 0 means they're perfectly similar, and higher number, more divergent they are. So we can like take pairs. So in, like we have K samples, we do like KC2, like pair side, 1 and 2, 1 and 3, 1 and 4. And with each pair, we can compute the DL metric and just plot, right? So in the first case, for temperature 1, right, it's mostly around the value 0. They're very close by. Some are diverging. In 1.5, interestingly, it's still close to 0, but it's less diverging. So although we expect to diverge, but it is not, right? So because it became more smoother, so the distributions are more close by. So temperature increasing is also sometimes good, right? 1.5 is giving me better response as compared to 1 because of more symmetry, more smoothness in the probabilities. But you go to even higher, right? Go to 2 and 2.5, they're very diverse, right? So definitely increasing all the way doesn't help, it like goes berserk. So with this, right, if we like, we can also zoom in, right? The same thing, let's focus on like temperature 1.5, right? I'll just zoom into this by a confusion matrix. So this plot shows, right, the same, I have 15 generation samples, right? 15 cross 15 matrix. 0 means like they were exactly same, higher number means they are different. So dark color means they were like same. So in this case, like out of 3 out of like 15, right, were different, this were all same. That means they were very consistent. But in the case 1.5, right, I have more colors over here. But interestingly, numbers right over there are, let's say, only few numbers like 1.311, that's a 0.4. So the variety of like these scores is less. It is more smooth and kind of telling me how my each sample is like kind of varying with the other one. So it's like a good way to zoom in to see how things are working. I'll now talk about like how to automate these things, right? So for automation, right? So we'll have the same thing, right? We have multiple layers. Each layer gives information. So like the first I get like sequence embedding, right? From the last token. Mid layer gives me like a semantic embedding, right? So for my response, if I like run multiple times, have k response, right? I can get k times the sequence vector, right? For each of these my responses. Now I have like k semantic vector for k response. Just do a matrix, right? The coherence matrix across all of them. So we like kind of collate them. I get a matrix. Simple thing basically k cross k matrix. Find an eigenvalue on them. Take an average, and that's my score. Let me just repeat the same thing step by step, right? So I'll just show this in like points, right? Same thing. First step, right? Again, take the last, right? So last layer mid vector, right? So that is because mid is the semantic information, right? So last token mid vector is something I want to look for because that contains the entire sequence and the semantic meaning of that. It's a d-dimension vector. Then like I take k samples. That's simple. I get the matrix, right? Centered by a vector called j, and then I kind of take eigenscore, and then take the average. So what happened in this, right? Just to understand the value of this. So like when the vector similar correlation basically, eigenvalue goes down. So like the higher correlation, lower value. So I'll get a value 0 for exactly same vector, right? So if my model is generating like very similar response, right? In that case, my eigenvalue will be very small value, right? But if they're very diverse, the value will be higher. So this score basically is kind of like a way to say hallucination degree, right? Higher the number, more hallucination. Lower number, less hallucination, right? So we can automate things by this. In this case, right, we chose things, but we can also automate, right? In a supervised way. That means we can create like features and ask the model to decide. So like a simple way, I have a prompt, right? Input prompt, we get a response, right? What do I have to take from, like output token? I have the probability of token, right? I have the entropy of the token, so I can use that. Then I can also have the embedding vector for a token. I have the semantic vector for a token, right? I can get this for all the tokens, right? So I have all this available, just some disposal, right? Because it's open box, I can get everything what I want, right? Now I can, for this, it's like one pair, right? One xi, yi. For one particular response, I can get all information from the model. I can like repeat multiple times, like k times. Like I get k pairs, input, output. And I can also define a ground truth, right? A reference score basically. That could be maybe like accuracy, precision, recall, F1, or like a blue score depending on problem basically, and get a score how good the response was. And all this we had, right? Can they become features, right? So all this becomes a features. I now just take the feature and the score, right? And contain a model. So that means with this like multiple training, this model can automatically, right, understand what's important. Like for example, in your case, accuracy is more important, right? So you can focus on that. Maybe some case the variety is important. So it can pick exactly what you train for, right? Your target is basically what it will learn from. So you don't think about, right, what you want to pick, it will pick automatically. You focus on that part. At runtime, just give the input, right, output features, and gives the model, you get a score. So this is like a more automatic way to focus on what's important for your problem, right? You just give a target variable, that score, it will align automatically based on all the information available. So with this, right, I think, yeah, it's like a complex thing. I'll give the thought and like pause over here and give like one more thought that how can we use this like application for reasoning, like in chain of thoughts. So as you know, right, we can have something called a think mode, right? Where the model can think more and like do more reasoning capabilities. But it's like a double-edged sword. Because like complexity increases brittleness, right? There was a study done recently. It was like a mass reasoning model. It like made one incorrect, right, analysis, and that caused like answer to go wrong 60% time. So like majority it went wrong because of one single like incorrect thing. So it's very fragile, right? So that's why we need to use it properly. One way is use it against the model, right? Like ask it, right, the error you made. This is something you can't do. Like for example, you did a choice A, that was wrong, right? You can say choice A, B, C are wrong. It can learn from that. That's a good way. And how can we find this automatically? By uncertainty, right? So with uncertainty, basically, we can say these choices are right, not clear, or more ambiguous. So we can automate this, right? And improve the reasoning on the model. Do more complex tasks and like do more complex things by agentic AI. That will make it more powerful. With this, I'll just conclude, right, with my final words. Simple thing, right? Don't trust the model, just test it, right? Because that's important. Uncertainty is like a metric to find hallucination. Find the right metric for application, right? So there are different things out there. You want to choose what's good for you. And in short, if you're building application, right, ask yourself, where will it break, right? And how can I find that before it matters? Because if you know it beforehand, you can model it and take care of that. So that like makes this AI more reliable going forward, and that makes it easier. With this, I'll conclude. Thank you very much. Yeah. Any questions? We'll be glad to take you. Yeah, please go ahead. Yeah.
Can you suggest or recommend us when we have to choose between small language models versus large language models?
I would say there's a very simple formula, right? If your task objective, that means like you have to find like entity, right? Very clear answer. Like get me the like medicine name, right? Get me the, let's say, type of cancer, right? Very clear objective, right? As compared to like what's probably create a new poem, right? Subjective basically. So for subjective task, go to LM, right? Objective task, go to SLM. So I think that's like clearly defined. Go to object task, like that's SLM over there. So objectivity is a key for SLM, and subjectivity is for LLM, I would say. That's a good difference, right? Like summary, right, where the answer is very crystal clear, right? You can like measure by numbers, right? Precision recall, basically, all those cases for SLMs. So to me, that should be the case for SLM.
Okay, so the objectivity and the correctness, you mean?
Yeah, exactly.
Okay, and then I have one more small question. With respect to some parameters which you stated about correctness, groundedness, relevance, I'm facing that challenge in my current project.
Yeah.
So do we have any standards with respect to the domain where we are developing the agents? For example, healthcare might be more expecting to have more accuracy over normal general Q&A assistants.
Yeah.
So do we have any such benchmarks based on your experience? Can you share that?
I think, yeah, because like they, as you said, right, they change from many right? Somebody focus more accuracy, somebody focus like more creativity. So in that case, you can define, right? So like as a judge, right, when you ask the LLM, right, to give a score, you can define, right? Judge on these parameters, right? So that's the way to judge it. But you can also define like the way it should end, right? You can make a model, right? What is amount to you? Just set a target, right? It will learn from that. So with the open box LLM, right, you can get all the features and define, right, what's good for your application, right? It will learn and take that score. And you get like a new agent, right, that scores your answer. Let's say in your whole in the AI system, right, you have a new agent that gives a score and says it's uncertain or not, right? And you can decide on that. So you can define that based on your own application by training it another model, right? A supervised model basically on these input features. So that can help you like customize to your application. Yeah.
So basically it is subjective to the area where we are
exactly.
working, but we don't have any such benchmarks.
Yeah.
Yeah, thanks.
Yeah, sure. Any questions? Yeah.
So when you talked about uncertainty, right?
Yeah.
So when we decrease the temperature, uncertainty will decrease, right? So upon multiple generations, answers will be consistent. But whether they will be correct or not, there is no guarantee, right? It can be consistently wrong as well.
Yes, that's correct. Yeah. So that's right. Remember the last part I showed you a score, right? From a reference answer. So basically we evaluate, right? Was it going right or wrong, right? Like from like SME, right? I can say, is the answer like correct? Like math problem, right? Very easy. Sum is correct, right? I know the sum, know the product, right? So based on reference score, right? I can define what is the accuracy of that, right? And I can use that as like a target variable, that score, right? To judge that answer. So all those features, right, can help it align. Is it going right or wrong? So you can train a model, right, based on the features also. So that way, kind of, you can see. But interestingly, if you look at the plot, right, in my case, 1.5 temperature, right, made it better, right? It was more like K11 was smaller. That means it was less varying. So smoothness sometimes also increases, right? It's not very clear. Like temperature low is consistent. Sometimes it's like more consistent at 1.5, right? But even higher, that goes diverse. So it's not a single answer, right? That you fix number to always take. So it's not like temperature 0 or 0.1 will always best, right? That's not the best case, right? So you have to play with that, and based on application, right, it will vary. So in short, on your application, I would say, make a like reference set, like ground truth. And on that ground truth, see what works better for your application using features. You can train a model and see what's good for you. So, yeah.
So the last two methods that we discussed, right?
Making model, right?
The supervised one and the hallucination.
Exactly, yeah.
They can detect hallucination, but not the uncertainty.
That's feature, right? It will use uncertainty to detect, right, basically. Those features are uncertainty features, right? So like that vector, like semantic vector, all those things, that contains uncertainty. It will use that information to actually model what you require, right? So the score you give basically, right and wrong, it will align with those features and solve what you want to solve from that.
Okay. Yeah. So do we have any libraries to calculate these, or we can?
Yeah. Actually, all these are papers, right? If you like search on ARXP, right, they Git repository for them, like, and you can just Google them. So they're ready papers on them. You can just download and use them. So just Google the same names, right? You'll get that semantic entropy, right? Be a name for them, and yeah, just download and use. Very easy.
Okay, thank you. Thanks.
Thank you, guys.
I have a question.
Sure, please go ahead.
This way.
Yeah, please.
So you mentioned that there are a couple of SLM models which are not currently being used, right?
Yeah.
But which are powerful models.
Yeah.
Like how can we know them? Which models are really used?
So I think key part is like you can customize them very easily, right? Like a BERT model, right? It's a very simple model. You can customize for NER, right? Position extraction basically. If you have data, that's the key part. If you have like data and labels, you can fine tune it very easily. Small models like 0.1 billion more, right? 100 million, 10 million basically. So download from like Hugging Face and just there's a like scripts to fine tune them. So if you have data, just download the script and fine tune.
Yeah, but if those are like domain specific models which are already pre-trained,
Yeah.
it will be easy, right? But how do we find out them? So there are like so many LLM models, right? SLM models in Hugging Face. So how can we know which one is the best one?
Like sometimes they decide like, or like biobot, right? That's basically biology, right? Then there's something like a financial bot, right? So based on that topic, right, describe what's the domain for that. So you can either pick that domain that's complying with your domain basically and fine tune it. Or you can also build from scratch, right? So like you can do like master modeling and like in my case, right, data, you don't find often, right? So for my ourselves, right, basically from the scratch, give like lots of documents, it builds a new domain. So it's very big or small, right? You can train very easily. So you can build your own domain or like search for Hugging Face. So both are options available.
Okay, and coming to the next question, so you mentioned like when we are trying to identify the word biomarker and lab.
Yeah.
So you mentioned that Bayesian technique is best. So do we have any relevant Bayesian SLM or LLM models in Hugging Face? Because I never came across or I don't know how to distinguish them.
Yeah.
So any idea will be
Talking
helpful.
about basically finding the uncertainty or finding basically the biomarker.
Biomarker, like whenever we talk about like similar kind of words, not only biomarker, if you talk about any general context, right?
Yeah, yeah.
The same word can be used in different contexts.
Exactly.
Verb, if you take a simple word, verb and adjective, right?
Yeah, yeah.
So when we talk about like medical, so the words will be like as you have shown.
Yeah.
How can you distinguish? Like, do we have any specific models to identify them?
So I would say like if you like have data, right? For example, in my case, if I like tag, right, this EGFR small case is lab, uppercase biomarker, right? For example, during training, you just show that to model, right? It will learn to differentiate based on context, right? Look at the context basically. That features will build up to differentiate. So just simple, like give that data with right label, right, and fine tune it. So it will learn automatically. So I would say that's the best one, right? Fine tuning is very easy, right? In these small models, like takes like half an hour, right? 1 hour basically. So add label the data and fine tune. It will find automatically. Not nothing required basically.
Okay, generally when we talk about passing the data to the model, right, we'll be either converting them from a large scale to smaller case, like this we'll be trying to do, right?
Yeah.
To avoid all the different keywords. For example, the way how the paper was written sometimes, or if it's a free text field, the way how it was written will be different, right?
Yeah.
So at that time we'll try to make them into single context, single casing. So at that time it will be tricky for us to identify, right? So is there any LLM model assignment which will be identifying based upon the context?
Yeah, that's like, because in this case also, like in the example I showed, right, biomarker and lab, right, it used the context, right? Remember there was like a market 25 MG, right? That word next to it was the context, right? It used that to differentiate. So it can find automatic, right? So in my case, I trained it, like fine tuned basically. I showed like that this is like a biomarker, right? This is like a lab. And use the context find, right? So it built embeddings based on that nearby words, right? And made different embeddings. So this is why, I think the key part is fine tuning, right? If you can have data, just fine tune. In case of SLM, right? It's very quick, very fast, nothing required, right? Just label the words, show it to it, it will learn automatically.